So good day, everyone. My name is Aga Rackiewicz, and I'm speaking to you on behalf of Yara International. Yara is a Norwegian company with a worldwide presence that we can describe as crop nutrition company. If you hear of crop nutrition, you can think of something like this, a bag of fertilizers. And you will be right. You can also think of all the factories where the fertilizers need to be produced. And you will also be right. Some of you, having read the topic of the presentation, might have thought of this, good-looking grains able to feed as many people as possible. And you would also be right. So in a simplified way, Yara is a company that produces and distributes fertilizers that travel to farmers' fields to help boost good quality food production. We also advise farmers on how to use these fertilizers and how to treat crops. So where there is space for a data scientist in such a specific industry like agricultural chemicals, are we as data scientists only enablers, or are we also generators of deep and useful insights? Can a mathematician by education like me be satisfied with working as a data scientist in agriculture? Well, it seems to be pretty obvious that if you are running a production company, you want to produce more and faster with maximum throughput. Sounds like wild capitalism, but data science can indeed help with that. In the past years, however, we can observe an increasing focus on other key performance indicators rather than just profit per hour. Companies care also about safety and reliability of production. And in addition, green production is not only of what we call corporate social responsibility, but it is such a vital problem that the norms were enforced by authorities, for example, by European Commission and the Green Deal. And the digitization through data science, among others, can help in achieving these traits as well. Life of a farmer is no more wearing dirty clothes and, in the best case, driving around the field in a tractor. A modern farmer is a businessman whose main working tool is a computer or a tablet. Digital helps making decisions both on macro level, like what crops to grow in which part of the field in what season, as well as on micro level, how much of fertilizer or water to apply where and when. At the same time, digital is present in the life of engineers and factory operators where the agricultural inputs are produced. Thanks to digital tools and data science, the engineer has easy access to data. They receive the recommendations for operating the factory in an optimal way based on the historically best decisions. And they can even get warnings if an equipment shows an early sign of failure. So what do I do as a data scientist? Data scientists sustain life of our assets, increase efficiency of our factories, and we also continuously strive to minimize the environmental footprint. You can even say that every day a plant runs stable is a good day for environment, or maybe not that bad. So how does such a good day of a data scientist look like? It's 8:30 a.m. and I start the day with a check-in with my team members. There's a new colleague joining the team, so it's a perfect opportunity to recap on the project's purpose. What you can see on the picture is a compressor, and such a compressor is one of the most vital pieces of equipment in an ammonia plant. Ammonia is one of the intermediate products of the entire process of production of the fertilizers that you can buy finally in the shops in the bags. If a compressor fails, or if we call it compressor trips, we need to stop the entire production, we need to shut down the plant and restart it again. So it's a both economic and environmental consequence. Therefore, we want to analyze the historical data to find patterns of anomalies that can be useful in the future for raising warnings about early signs of potential failure. And for that purpose, we gathered 160 sensors and 3 years worth of data. But we don't know how many anomalies happened in the past. Only few of them are labeled by the experts. So that means we encounter an unsupervised learning problem, which is naturally more challenging than the regular supervised ones. But thankfully, one of our colleagues offers us help, and at 9:30, we get invited to a knowledge sharing session. We call a colleague overseas, as we are quite a distributed team, and he will tell us about a neural network-based approach for detecting the anomalies. It's called autoencoder. It tries to learn a smaller representation of an input through the encoder part, and then recreate it through a decoder part. And in a similar way as to the images, that is a pretty natural way of thinking of neural networks, hey, unstructured data. We can also use it for time series, in fact. So we first learn the neural network on the normal phase, which we would call a training set. And then we apply it to the test data, and there we hope to find some anomalies through a simple scoring system. So every timestamp gets a score assigned. And if a score is high enough, that means there must have been an anomaly at that time. This is how a sample output looks like. So in this case, 96 sensors constitute an input, which makes it naturally more powerful tool, the autoencoder, a naturally more powerful tool than simple univariate models that are able to detect only point anomalies or maybe some kind of like level shifts or pattern anomalies, but within a single sensor. Here, the model returns an anomaly score, which is a sort of an aggregate of all these 96 sensors, together with several timestamps where a threshold was exceeded, a threshold for an anomaly. And additionally, we get something like a feature importance. So these are the sensors that contribute the most to the high anomaly score. And looking, let's say, at the first period of anomaly, we can dig into the root causes. And we are looking closer at one of the top contributing sensors, and we compare it with the expert detected anomaly. And indeed, the model seemed to have correctly identified an anomaly, which gives us quite high hopes for success in the future as well. For the rest of the day, I'm going to work on a different project. This time we are moving to a nitric acid factory. And nitric acid is another intermediate in the process of finished fertilizer production. We want to understand the cost components of nitric acid production. And one of these costs that we are going to review with an engineer today is cost of greenhouse gases emissions. So you can think of CO2, you can think of N2O. So these gases, definitely we want to kind of minimize the emission. It's also a cost that is enforced by the regulations. We would like to understand what is going to be this cost in relation to how much we produce of this nitric acid, so what we call production load. Normally, such a review would take place in a factory itself, which is definitely one of the most fun and cool parts of working as an industrial data scientist, that you can go to a factory, wear a helmet and safety shoes, and walk around the place where you actually kind of work, but on a regular basis remotely. But of course, given the circumstances, we have to stick to a regular video conference. And thankfully, this time a simple regression model does a good job. So we can focus on what I personally, as a data scientist, like the most, that is reviewing insights. With machine learning model, we can give a precise recommendation about the optimal operating set points to balance the amount of the production and the cost of greenhouse gases emissions. In addition to that, depending on ambient conditions like temperature and pressure outside. And data scientist does not only deliver a Jupyter notebook with a model and some calculations to an engineer, but we also participate in process of designing software that the engineers are going to use. So, maybe some of us don't have the strongest sense of aesthetics. See my slides. But we know what at least is possible to show as a calculation and what is not. After lunch at 1 p.m., I finally have some time to quietly work on a model that I currently build. And I want to connect the amount of steam produced by nitric acid factory with the amount of ammonia consumed, which is kind of proportional to how much nitric acid you produce. Why is it so important? So production of nitric acid is such a energy-rich reaction that it produces massive amounts of steam, but there are some other production units located in the same place that need this steam to be consumed. So we need to understand what is the steam balance. And if it happens that there is some extra steam left, we can send it to electricity generator and convert it to electricity and use it in the plant instead of buying more from the grid. Perfect, we have quite a rich data set. Yeah, the task seems to be straightforward. We have ammonia consumption on the blue and steam on as orange. But if you look closer, you can see that at some point of time, the orange line does not follow anymore the blue line. And that means that there was some structural change in our data. The model, if we train the model on our first 80% of data, it would not work well on the last 20% if we could consider it as a test set. So instead of building a regular neural network, we aim to decompose the time series to capture both long and short-term behavior. So we learn the overall underlying behavior before this structural change, for example, to understand the seasonality, a bit of the interactions with the ambient conditions. And afterwards, we transfer these learned weights, fine-tune the last couple of layers in the neural network based on a short-term data set to capture those possible structural changes. And finally, we use this fully trained neural network to predict the future. And this approach is called transfer learning. I bet that it's not the first time today that you have heard about that. It's widely used in heavy industries where we encounter structural changes in our time series behavior, being it turnarounds in the factories. Turnaround is a period of plant shutdown and maintenance, or changes of unknown origin, like for example, in petrochemicals, where in addition to equipment itself, you also have the components of geology, for example. And definitely, you have heard more about this approach in the very morning today. And by the way, what we have discovered thanks to this model is that in the next day, there will be some steam available. So we don't need to buy so much electricity from the grid. We just have to send it to generator, and the electricity costs will be reduced. So it was quite a long and intensive day full of many strange time series, which are the most common problems that it seems that we are dealing with on a daily basis. It's time to do one last check of our intranet and slowly close the day. Oh, but there are some interesting news on intranet. I found an article about AdFarm. It's a precision farming app developed by Yara. And imagine that by taking a photo of your crops, it's able to estimate how much nitrogen do the crops need for optimal growth, because there are some visible signs of lack of nitrogen in, let's say, crops' leaves. So that actually sounds a little bit like science fiction, but it's really true. I definitely have to make sure to connect with that team and check more details in the future. So overall, was it a good day? Well, I managed to help run the equipment smooth. Check. I reduced the greenhouse gases emissions by giving hints to the engineer for the optimal settings of the plant. Check. And I reduced electricity consumption in the plant by making use of the available steam. Check. So have I saved the world? Maybe a tiny bit. Do not hesitate to reach out to me in case of any questions about Yara, about my digital production department and the growing team that I'm part of. Thank you very much for the attention.